composition rocks and start to react them, you form monomineralic layers. And that's what Bernie and I tried to reproduce in the lab. We put an eclogite near the peridotite, and basically on methods of Korzinski, you would have a garnet layer by the eclogite and the enstatite or orthopyroxene layer by the peridotite. So, and of course, this garnet near eclogite would actually be of different composition that you expect for the eclogitic component composition. So what we've done, this experiment, and of course, because we were lazy and we didn't run it for a week or two to actually show an amazing monomineralic layer, we showed that reacting peridotite with eclogite, and to actually flux the reaction, we added a little bit of carbonate there, we form this layer of orthopyroxene exactly like predicted by Korzinski, and then a layer of garnet by the eclogitic side. And this garnet is really magnesium rich, and it also plots on this pyroxenitic trend, even though it's adjacent to eclogite. So these two papers, a paper of with Bernie and Thompson, came out pretty much at the same time, showing that reacting carbonate-bearing eclogite with, let's say, adjacent peridotite, you can form some hybrid intermediate and composition rocks. So, and I will conclude here the first part of the talk about the compositions and the lithologies in the transition zone. I probably didn't really shed light on the entire mental transition zone composition, but I can say that you can use theoretical trends for majorite garnets as an indicator of the bulk composition rock. And this, I'm really happy that this paper by Bayer and Frost has just come up in EPSL, I think, and they showed exactly the same, that they ran a range of compositions exactly plotting these two trends. The highest pressure majoritic inclusions are pyroxenitic, and there is actually not a single peridotitic inclusion so far found from the mental transition zone. All of them are lowermost upper mental, but not as deep as transition zone. There is possibly that pyroxenite diamond association is because of the interacting between basaltic and peridotitic compositions. And these two papers by Thompson et al., who showed reaction of carbonatitic melt with peridotite, and us putting two layers together, they agree in their results. So the second part of the talk, a much shorter one, I want to talk about the oxidation state of the mental transition zone. And I have to say that some of the data is still fairly raw, and we're still trying to figure out the relationship and the results, but I find it incredibly fascinating and certainly very interesting. So there are kind of, although these two they are not really controversial to each other, there are kind of two lines of evidence that diamond growth can form in very reduced environment, like a paper that recently came out in Science by Smith et al., who showed that the diamonds can crystallize from Fe and ICS melt, which would be well more reduced than iron wustite. And the second one, that diamond growth can come from the carbonatitic melt, an idea that was proposed and I would say chewed up and churned in literature over the past 2 decades. So this, even though it is relatively more reduced or oxidized, it can still be happening in quite a reduced mantle. So the idea generally of the transition zone redox state is shown quite well in Robach and Schmidt paper in 2011, that most of this mantle is controlled by the iron wustite buffer. So no trivalent, so all the iron metal is present in this part of the mantle. It's stable. Then, due to the disproportionation, the FeO is basically turning into Fe and Fe3+. Fe3+ goes into the garnet. Fe stays at metal. So then, if you, to this area, introduce a slab, a fairly oxidized slab, you trigger the reaction of carbonate in the slab with Fe metal present in this area. And because there is much more Fe metal than the carbonate, you kind of freeze all these carbonate and form diamond until there is an upwelling and all the redox reaction goes back. So just to cut the long story short, you have Fe metal you have carbon and you have some wüstite NGO in this area, and the garnet should be rich in trivalent iron. So now, what we're trying to do next, we collected or picked 13 inclusions, majoritic inclusions in diamonds. They are all pyroxenitic, and they span over the range between 8 GPa and 18 GPa in pressures, coming on this trend. And all these inclusions have previously been studied for carbon isotopes and for oxygen isotopes, which showed quite a good correlation with having this carbon from the, coming from the subducting slab, really low light carbon isotopic signatures. So we took these inclusions and tried to analyze and to measure ferric iron in them. So how we do that, we use this a really amazing, fascinating thing. Don't ask me how it works, because it's really crazy. It's the Synchrotron Mössbauer source. So I'll try to explain it really primitively, as much as I understand the physics behind it myself. Like if we have a typical classical Mössbauer, we have a radioactive source, let's say cobalt-57. It breaks down into iron, decays iron-57, emitting a gamma quant. This gamma quant is absorbed by our sample, and then we measure the spectrum. And on the spectrum, we can see a clear difference between ferric iron and ferrous iron. So one of the bad or kind of flaws of this sample, of this measurement, is that the beam is really large. It's about 200 microns. So we cannot analyze samples which are lower in size, or smaller in size than that. However, our majoritic inclusions are between 30 and 100 micron size. So it wasn't possible to analyze them before, until this really amazing technique has just come recently for the use. So when we're talking about synchrotron, we have all these electrons being accelerated along the kind of ring. So then, due to the magnets, they are moving along a sinusoid, having certain electromagnetic waves. So, and these waves have the entire range of frequencies. However, we need very, very small frequency to use for our sample in the Mössbauer. So what they do, they use all these monochromators or kind of crystals to reduce the amount of, actually to make the spectra or the frequency to reduce it to the one that we need. So it comes from 2 electron volts, which is really big, then to milli electron volts, and then ultimately to nano electron volts. So to generate this Fe57, they're using an iron borate crystal. And again, to just avoid the diffraction, they're using a certain crystallographic axis. So, and along this axis, there is no diffraction, but just a pure nuclear reflection from this crystal. Then it goes onto the sample, and then the focus beam is just as small as 30 microns. So that enables us to use this technique for analyzing majoritic inclusions. And we don't even need to extract them from the diamond. They can be used in situ. Although we did extract them, but that's not necessary. And this is the resulting spectra. So the bigger is this doublet of ferric iron, the more ferric iron is in the sample. So this is our Fe2 plus area, Fe3 plus area, and for the inclusion at 8 GPa, we get about 7% of ferric over ferrous over total iron. So then, once we increase the pressure, that's about 11 GPa, you can see that the doublet is slightly bigger. It's 13 over ferric iron over total iron. Another one, this shows 16 GPa, it's 30% of ferric over ferrous, and you can see how big the doublet is. So ultimately, we end up with our inclusions having an absolutely amazing trend with pressure, showing from 8 GPa to 18 GPa, the trend increasing in ferric iron from 8% to pretty much 30%. And amazingly, this trend actually follows the one that was described for the xenolith, garnet xenolith from Upper Mantle. And of course, here is a huge spread, and these are the papers published over the last 20 years, and some of the higher values were reported as being metasomatized, which would inadvertently increase the ferric iron. But nevertheless, it reminds me of that paper by John Blundy in 1990, who showed that all the upper mantle is controlled by CCO, carbon-carbon dioxide equilibrium. So when I'm looking at this trend, I'm thinking, is it true that the transition zone is also controlled by the CCO buffer? So now, the hard part follows. We need to convert all of these ferric ferrules into the actual oxygen fugacity. So, which is a bit of a problem, but before I do that, I refer again to an old paper by Wood et al., who predicted that not necessarily due to the ion disproportionation, but also due to the reaction of carbonate with ferrous ion, you can increase the ferric ion component in the majorite, forming a skyagite garnet, and reduce the diamond. So if you have carbonate, you reduce the carbonate into diamond, and at the same time you need to oxidize divalent ion into the trivalent ion. And the only phase that can take the trivalent ion is garnet. So following this reaction, unfortunately, it doesn't work for our cases because it involves olivine. And given that our compositions are kind of more like intermediate, we're not too sure whether it's in equilibrium with olivine. So the another thing which was shown by McCammon et al. Is the increase in ferric ion with actually decreasing alumina content. And it also shows quite well that ferric ion sits on the octahedral side of garnet. So the last thing is my probably quite a petty attempt to put these majorites on the some kind of equilibrium and oxygen fugacity plot. So what I'm trying to do here, and I have to say in advance that F and Q just won't work. And it won't work basically because quartz doesn't exist at those depths. Fayalite also doesn't really exist at those depths. So using F and Q or even fayalite magnetite stishovite wouldn't work very well. So the equilibria that I have to come with should be a little different. And there are two reactions I've used so far. One is to actually put the majoritic inclusions, and the other two are just to show the buffers. So the majoritic inclusions, ideally, would be good to use just the garnet components. But because I cannot find a reaction for that, I have to put a stishovite as well. So it uses grossular element in majorite, andradite, and pyrope. And again, using the Holland and Powell database, I come up with these log FO2 values. There is quite a discrepancy at lower pressures due to the very small majoritic component in garnets at those pressures. But generally it looks pretty good. So the other two oxygen fugacity buffers are using carbonate. And the simple one is GMDS, which is magnesite, garnet, stishovite, and diamond. It's very simple, and there is hardly any room for making a mistake while putting that equilibrium. It lays very, very close to our garnets. And the top one, the green one, is exactly the same as this, but with aragonite. And again, to mass balance this reaction, it had to be slightly more complicated. So this is very preliminary data. Basically, don't kill me for it. It's much higher than einhustite. And I still cannot really reconcile why these inclusions are in the transition zone where we should be buffered by the einhustite, yet on this diagram they are sitting about 5 log units above it. And I think I'll finish with that, saying that there's still quite a bit of puzzle, yet I'm quite confident with the fact that these are the first measurements of majoritic inclusions in situ for ferric ferrous ion. They do prove the fact that the deeper we go, the more ferric ion enters their structure. The way why that happens and the reason is either because of the simple ion disproportionation. However, seeing how close and how right they sit near the carbonate equilibria tells me that they must be linked to the carbonate reduction into garnets through Fe oxidation into ferric ion. And basically this is it. Thank you very much for your attention.
Questions? First, I want to thank you for a really great talk. I really, really liked it. So this is kind of an off-the-wall question, but many times people have suggested that, for reasons that I'm not particularly convinced would be right, is that carbon, for whatever reason, prefer to be tetrahedrally coordinated to oxygen at depth. And it just seemed to me that these major conclusions, using maybe like carbon zanes or something, would be fascinating things to look at, because if there was ever a case where you had the activity of carbon being high enough, that if there was a reason why you want to make, we call it orthocarbonate in organic chemistry, to put an orthocarbonate substitution for silicon, it might be in majoritic garnet inclusions in the diamond host, because if it doesn't happen there, then in principle I would imagine it doesn't happen anywhere.
So do you think that these can actually have carbon, like diamond having, garnet having carbon in its structure?
Well, what I'm proposing is, sorry. Well, it's my wife, so be careful. So a number of people come in and speculated that, oh, well, maybe at really high pressures, carbon dioxide, which can exist, you would think of it as a trigonal form, but you can also form even a
tetragonal, as you
the
said,
tetragonal, we call it orthocarbonate. Would that substitute for silicon? And nobody knows, but I've seen people speculate.
No, like it's a thing that I've never thought about actually.
Well, I'm just saying that
really,
it seems to be those majoritic conclusions would be the best place to look for that substitution, because you've got the benefit of the highest activity of carbon that you're ever
wouldn't work. I tell you why. We've analyzed these inclusions by diffraction on Petra to actually make sure that they are monomineralic. Because when you analyze by Mössbauer, you never know whether there is one phase or two phases or three phases. Maybe they have already broken down into some kind of hematite, or I don't know, or even orthopyroxene that contains higher trivalent ions. So to make sure that when analyzing a monomineralic assemblage, we did diffraction on Petra, and it was absolutely perfectly correlated with the structure of majorite. However,
I think this would be so low. I mean,
probably you're right.
You
Yeah,
never see it.
Yeah.
Well, I don't want to derail it, and I do got to call my wife, but I'll come back to this.
Well, it could be done with C13 dope, but that's actually what Synchrotron D and I have been doing, trying to see, various was MR actually. That's his expertise to look at. But anyway, other questions, comment.
So you're worried about your estimates of the FO2 being very high?
Yeah, I'm worried indeed.
But surely what you're recording is the FO2 in the fluids, not the ambient transition zone. Since you're reducing you're producing the melts and doing much of the reactions by having CO2 being fluxed off and coming off of your mantle, of your conducting slab. It's not necessarily telling you anything about the ambient mantle conditions, just the fluid in which the diamond is forming.
Well, yes and no. So there was a paper in 2007 by Robach and et al. In Science, and what they did, they ran majoritic assemblage in iron capsules, and they crystallized pure metal, iron metal. They doped it with a significant amount of FeO, and they ended up with metallic iron in equilibrium with majoritic garnet that had really our values of trivalent iron at very similar pressures. So by using disproportionation reaction, they actually showed that at pressures they can put quite a lot of ferric iron into the garnet, at the same time reducing FeO into Fe. If we look at their data, we can certainly see that they're below iron boostite, right? So yet both our inclusions and their majorites, experimental, have identical ferric iron content. I'm saying identical, there will be a little shift, but it's irrelevant. So what I'm trying to say that how come two majorites with, let's say, 30% of ferric iron be here and here at the same time? This is something I can't explain, and I've been scratching my head over that for a while, and eventually well, we'll figure something out, because obviously experiments and real data are two different things, and when you're under controlled environment, it's a totally different story. But
if you apply these two buffers to those experiments,
oh, they don't have carbon.
Okay.
They don't have carbon. I can't.
Well, I mean,
Yeah, but I see your point. It's actually, you're probably right, and I'm pretty sure that these inclusions are quite oxidized. So the only thing, I just, maybe there are two different ways of increasing Fe ferric content in garnets through two different mechanisms, and this is something is yet to be confirmed or tested.
I think that's, I just want to answer before I call you. And it's definitely, I agree, you know, there are probably different mechanisms. We're looking at the redox reaction or the general mantle oxidation state. It's two different things.
Yeah.
Obviously, this too could be reconciled because you have carbon, and because of redox reactions, you can even get higher ferric ion. Actually, we have some result which we can talk about. But the mantle, if you find a majorite in a rock without, not as a carbon diamond inclusion, that probably will tell you more about this ambient, you know, the general mantle conditions. And Steve.
That was not my wife calling. So, you know, if we have a slab graveyard in the transition zone, it doesn't seem inconceivable that we could have reducing and oxidizing regions. We just have to separate them for long enough. And so I think what your answer and Faye's comment and Connell's question, you know, are segueing to the idea that, you know, you have regions of the mantle that are grossly different in oxidation state.
This
So
is something else.
we're going to have to buy that, and the question is, how do they relate to each other, and are they related to a geologic kind of process where they're connected in some sort of continuum in the carbon cycle, or are they just heterogeneities that exist for a long time? That's kind of where I sort of see this kind of thing going.
Yeah, I fully agree with you. I also think that you cannot take the transition zone as one entity that has always iron metal present there, or kind of saturated in iron metal, let's put it this way. I do intuitively disagree with Robert H. Schmidt big model, big picture, but up until now I didn't have any proof or actually showing that it not necessarily works in all the conditions. So, however, saying that diamond crystallization is, or what we see here, is a very rare, I'd say, process that doesn't necessarily speak much of the entire transition zone, but some local processes, diamond forming related. Yeah.
Any other questions? So Kate is going to be here. And
Could you say what the subject of the talk for tomorrow will be?
Oh, it's sulfides in the mantle and chalcophile element partitioning between sulfide and silicates, with the implications for mid-ocean ridges and earth accretion.
Do you want to think about maybe seeing about getting this ACC, because you've got a little more room? Boy, could get kind of tight.
It's going to be a shorter talk, I promise.
Yeah,
I can see
there
where
will be a more informal discussion too. So, but
ACC would be good.
Yeah, because I could see where more people than you might think for Boyd might show
okay.
up.
So I can send an email out that just says we need to check if ACC is available. I only reserve the board. So if ACC is available, I'll send another email out. Okay, let's thank.
I didn't rush. Did I?
No, it's that was the right balance.
Yeah.
Yeah, well, he's part of, he's doing the experiment. He's my first time.
Oh, I didn't know that. Okay, because I've seen the AGU.
Yeah. So that's the experiment part. But I've been working with.
Can you show me more of it?
Yeah,
I mean,
yeah.
if it's not secret.
No, it's acceptable publication.
Oh, great.